Hello everyone. I hope you have been following the lecture series so far and that you are finding them helpful. In the previous lecture, we introduced the motivation for studying linear algebra in the context of control systems. Control theory fundamentally relies on linear algebra structure since many dynamical systems can be described using linear equations or in state space form. Even though real-world systems are often nonlinear, linear algebra provides the language, tools, and approximation techniques that allow us to analyze, design, and control such system effectively. In the last lecture, we started our journey into the linear algebra by talking about some fundamental definitions. We said that a vector space is a set X over a field F. We show that X and F together with two operators, vector addition and scalar multiplication. These two operations must satisfy certain rules called axioms. Here, members of X are called vectors and members of F are called scalars. First, X must be closed under both operations. That means if you take two vectors u and v from X and add them together, the result is still inside X. And if you take any vector in X and multiply it by a scalar, the result is also inside X. Second, the operations should behave distributively. It means if u and v are in X and alpha is a scalar, then alpha times the sum of u and v must be the same as alpha times u plus alpha times v. Similarly, if alpha and beta are scalars and u is a vector, then the scalar alpha plus beta multiplied by u must give the same result as alpha times u plus beta times u. We also required associativity of scalar multiplication. That means if we multiply u first by beta and then by alpha, the result must be the same as multiplying u by the product alpha times beta. After that, we define the concept of a subspace. We say that Y is a subspace of X if Y is a subset of X and if itself a vector space under the same two operations, vector addition and scalar multiplications. We then move on the linear combination. A linear combination means creating a new vector by scaling some existing vector and then adding them together. For instance, if we have two scalar alpha and beta in F and two vectors u and v in X, then we can form a new vector y equal alpha u plus beta v. This leads us to the idea of linear independence. A set of vectors is linearly independent if no vector in the set can be written as a linear combination of the other vectors. Formally, if the only way to form the zero vector out of combination of these vectors it's to choose all coefficients equal to 0, then the set independent up to xn. Suppose we have vector x1, x2 all the way to xn. Imagine we form a linear combination as a1 x1 plus a2 x2 so on up to an xn. Oh, it should be this. equal to 0. If a1 is not 0, assume a1 is not 0, we can solve this equation for x1. x1 is equal 1 over a1 minus a1 plus a2 times x2 to an times xn. In the other word, x1 can be written as a linear combination of the rest. This means the set of x1 to xn is linearly dependent because we define one of this vector with respect to other vector. So the key takeaway is, if even one of the coefficients in such an equation is non-zero, then the corresponding vector can be written as a combination of others, which makes the set dependent. Otherwise, if the only solution is that all the coefficients are zero, then the set is independent. After we introduce the idea of linear independence, we define the concept of the dimension of a vector space. The dimension of a vector space X over a field F is the maximum number of linearly independent vector that can be found inside X. For example, if the maximum number of linearly independent vector in X is 3, the dimension of X is 3. Now, since we can often express some vector in terms of others, it's natural to ask, why not choose a special set of vectors and define every other vectors in the space with respect to this set? This leads us to the idea of bases. Formally, a set of vectors e1, e2 all the way to en is called a basis of vector space X if two conditions are satisfied. This set is linearly independent, and every vector in X can be written uniquely as a linear combination of e1 throughout en. The word unique is very important in this definition. This means that for each vector in X, there is one and only one way to express it using this basis vector. When we write a vector in terms of this basis vector, the coefficient that appear in front of the basis vector called coordinate representation of the vector with respect to that basis. Our important point here is that we don't have any restriction on which basis vector we choose. Any set of n linear independent vector in X will form a basis, where n is the dimension of the space. Because of this freedom, the same vector can be different coordinate representation depending on which basis we use. In other words, if we switch a new basis, the same vector will be represented by a new set of coordinates. Finally, we answer a very natural question. If we choose two different bases for a vector space, is there any relation between the coordinates representation of a vector with respect to these two bases? The answer is yes. The relation is governed by what we called a change of basis matrix. This matrix converts the coordinate of a vector from the old basis into its coordinate in the new basis. Here is how it works. Suppose we have two bases, the old one and the new one. To build the change of matrix P, we take each vector from the old basis ei and express it in terms of the new basis e bar 1 all the way to e bar n. The coefficients that appear in this expression form the column of the matrix. So the ith column of change of basis matrix is exactly the coordinate representation of the ith old basis vector expressed in terms of the new basis. Once we have this new matrix, we can easily translate the coordinates of any vector from the old system into the new system. Now, it's time to dive into our idea of linear operators. First of all, a linear operator is just a kind of function. When we say operator, we simply means a function, but usually with some extra structure. Let's recall what a function is. Suppose we have two sets, x and y. A function f from x to y is a rule that assigns each element of x to exactly one element of y. So if we take an element x from the set x, then f of x is a specific element of y. We denote this by y equal f of x. In this language, the set x is called the domain and the set y is called the range. Sometimes in books, you will also see the word codomain used instead of range. Now, when we say a linear operator, we want to specify a very particular type of functions. A linear operator is a function where both the domain and the codomain are vector space over the same field. In other words, it's a function defined on a vector space and mapped into a vector space with one special property, linearity. Let's call the operator L if we pick two arbitrary vector x1 and x2 in the domain and two scalars alpha 1 and alpha 2. Then linearity means to take the combination alpha 1 times x1 plus alpha 2 times x2 and then apply the operator L to it. The result must alpha 1 times L of x1 plus alpha 2 times L of x2. If a function satisfies this property, then we call it a linear operator. Let me give you a simple example. Consider a function that rotates a vector in the plane. Let's call it r theta. This function takes any vector in the plane r2 and give us another vector in r2 that is rotated by the angle theta. Now, if we take two vectors, for example, x1 and x2, add them together and then rotate like this, the result, we get exactly the same outcome if we first rotate x1, then rotate x2, then add the result of rotated vectors like this. So rotation by an angle theta is a linear operator because it respects these linearity rules. Let's continue with our example of rotation by an angle theta. Assume we define two orthogonal basis vector e1 and e2 for R2. Now, any vector in R2 can be expressed in terms of this basis as two numbers x1 and x2. Suppose we apply our linear operator rotation by theta to x, we call the result y. Just as we express x in terms of e1 and e2, we can also express y in terms of e1 and e2 with coordinates y1 and y2. We can derive the relation between y1, y2 and x1, x2 with respect to the angle theta. y1 equal x1 times cosine of theta minus x2 times sine of theta. y2 equal x1 times sine of theta plus x2 times cosine of theta. We can package these formulas neatly into the matrix. We define the matrix R theta, which looks like this: cosine of theta, negative sine of theta, sine of theta, cosine of theta. When we multiply this matrix with clone vector x1, x2, the result is the clone vector y1, y2. So in this case, our linear operator, rotation by theta, can be represented exactly by the matrix R theta. Now a very natural question comes up. Is this always true? Can we always represent every linear operator with a matrix? Or is this just a special case for rotation? The answer is yes. Every linear operator can be represented by a matrix. And that is one of the most important reasons we treat linear operator separately from general functions. At the beginning, I said a linear operator is just a kind of function, but the reason we study them in depth is that they have this very special property. We can always represent them in the form of a matrix, and matrices are very convenient to work with. Here is the formal statement. It's a theorem. Suppose x and y are vector spaces over the same field F. Let the dimension of x be n and the dimension of y be m. If we choose a basis of m vectors for x and a basis of m vectors for y, then any linear operators L that maps x to y can be represented by an m by m matrix A with entries in F. Concretely, this means if we take E1 throughout En as a basis of x and V1 throughout Vm as the basis of y, and we represent a vector x in x space by its coordinate x1 throughout xn in this basis, and the y equal L of x is represented by in y by coordinate y1 throughout ym, then there exists a matrix A such that the coordinate vector y1 throughout ym equal A times the coordinate vectors x1 throughout xn. Because dimension of left hand side is m and dimension of x is n, A should be m by n matrix. How do we can actually define this matrix? This is a very important question, because if we can find A, we don't need to carry the linear operator with us everywhere. We can just do matrix manipulations, which are much easier. So let's see how we can do that. We know y is equal L of x, and x itself can be written as a x1 times e1, x2 times e2, all the way to xn times en, where e1 throughout en are the basis vector of our domain. Now, because L is a linear operator, we can distribute it across this sum that gives us y equal x1 times L of e1 plus x2 times L of e2, and so on up to xn times L of en. This is a key step. It tells us that the action of L on any vector x is completely determined by what L does to the basis vector e1 to en. Next, notice that L of e1 is not just any vector. It lives in the codomain y, and y itself has a basis. So each L of ei can be written as a linear combination of this basis vector v1 throughout vm. Concretely, that means L of ei equals a1i v1 plus a12i times v2, so up to ami times vm. ai throughout ami form the coordinate of L of ea in the basis v1 throughout vm. If we arrange v1 throughout vm as a clone of a matrix, it's called capital V, then each coordinate vector ai, the one with entries a1i throughout ami, tell us how L of ei can be written as a v times ai. Now let's put this back into our earlier equation for y. Instead of writing L of ei directly, we write it as a v times ai, like this. And we can factor out the matrix V, like this. From this, we see that in coordinate form, the vector v1 throughout vm is equal to the matrix a1, a2 to an times the coordinate vector x1 to xm. And there we have it. We have found matrix A. Because this part and this part are the same, then this part should equal this two parts. The matrix A is built from the coordinate vector of L applied to the basis vector of x. expressed in terms of the basis vector of y. Each column of A is exactly the coordinate representation of L of EI in the basis of y. So to summarize, given basis for the domain and codomain, the matrix A represents the linear operator. Once we have A, we can map the coordinates representation of any vectors in linear space X directly to the coordinate representation of a vector in Y using simple matrix multiplication. A broad and very common case of linear operators is when the operator maps a vector space into itself. Consider an operator L maps vector space X over field F back to X over the same field F. A simple example of this is our rotation operator by theta. It takes a vector in R2 and produce another vector in R2. In other words, it maps R2 to R2. In this case, if we write y equal L of x, the both y and x are in the same space X. Because the domain and codomain are the same space, we can use a single basis for both sides of linear map. For example, suppose E1, E2 up to En are bases of x over f, then we can write the coordinate of x as a x1 throughout xn and the coordinate of y as a y1 throughout yn. The relation between them is given by y equal a times x. Here A is an n by n matrix because both the domain and codomain have the same dimension. In this setup, the ith column of the matrix A is simply the coordinate representation of L applied to basis vector EI expressed again in terms of the same basis E1 throughout En. In this setup, the ith column of matrix A is simply the coordinate representation of L applied to the basis vector EI expressed again in terms of the same basis E1 throughout En. Now let's go one step further. Suppose we introduce another basis for the same vector space X. Let's call this new basis E bar 1 throughout E bar n. As already mentioned before, for any vector space, we can define many different bases. And depending on the basis we choose, the coordinate representation of the same vector will be changed. So for both x and y, if we switch to the new basis E bar throughout E bar n, we get new coordinate representation. Let's call this coordinate x bar 1 throughout x bar n for the vector x and y bar 1 throughout y bar n for the vector y. With these new coordinates, the linear operator is expressed using another matrix. Let's call it a bar. Therefore, based on this, we have y bar equal a bar times x bar. Now I want to ask another question and answer in the follow. What is the relation between a and a bar? We know they both represent the same linear operator L, just expressed into two different bases. But how exactly are they related? This is an important point because it leads us directly to the concept of similarity transformation and the change of basis relation between two matrix representation of the same linear operator. Now remember that the coordinate vector x1 throughout xn and the coordinate vector x bar 1 throughout x bar n are just two different representations of the same vector x. One is written in the term of basis e1 throughout en, and the other is written in terms of the new basis e bar 1 throughout e bar n. Because they are two ways to expressing the same vector, there must be a relationship between them, and the relationship is given by the change of basis matrix. So P is the change of matrix that convert coordinates from the original basis e1 throughout en into a new basis e bar 1 throughout e bar n. Then P inverse does the opposite conversion. It takes coordinates in the new basis back into the old basis. That means we can write the relation like this. The coordinate vector in the new basis x bar 1 throughout x bar n is equal to P times the coordinate vector in the old basis x1 throughout xn. And equivalently, the old coordinate x1 throughout xn are equal to P inverse times the new coordinate x bar 1 throughout x bar n. And of course, the same relation holds for y. And of course, the same relation holds for y, because y is in the same vector space as x. Its coordinate representation in the original basis and its coordinate representation in the new basis are also related by the same matrix P. So y bar equal P times y, and y equals P inverse times y bar. Now let's connect everything we have said. Earlier, based on basis e1 throughout en, we defined the matrix form of our linear operators as A. So in that basis, the relation was the coordinate vector y equal A times coordinate vector x. But remember, we also know the relation between the old coordinate and the new coordinates. Specifically, x equal P inverse times x bar and y equals P inverse times y bar. So let's substitute this into the equation y equal ax. On the left hand side here, instead of y, we write P inverse y bar. On the right hand side, instead of x, we write P inverse x bar. That gives us P inverse y bar, a P inverse x bar. Now multiply both sides on the left by P. We get y bar equals P times A times P inverse x bar. This is exactly the matrix relation had in the new basis. Y bar equal A bar times x bar. Comparing the two, we see that A bar must be equal P times A times P inverse. So we can exactly do the reverse. Start with y bar equal A bar x bar. We conclude that A must equal P inverse times A bar times P. So we now have a very important result. The matrix A and A bar are related by the equations A bar equals P times A times P inverse, and equivalently P inverse times A bar times P. This relation is so important that it has a special name in linear algebra. We say that A and B are similar matrices if there exists a non-singular matrix P such that A bar equals P times A times P inverse. This is a very good news because it means that all the different matrix representation of the same linear operator when expressed in different bases are similar matrices. In the other words, similarity tells us that although the number inside the matrix change when we change the basis, the essential structure of the linear operator remains the same. In future, when I will introduce eigenvalue and eigenvectors, I will show you when two matrices are similar, they share the same eigenvalues and the same eigenvectors. And because eigenvalues and eigenvectors capture the fundamental behavior of a matrix, in fact, the underlying linear operator hasn't changed. Only the coordinate system has changed. Let's go back to our example of rotation by an angle theta. Recall that in the standard basis, that is the basis vector 1, 0 and 0, 1, the matrix representation of the rotation operator is r theta. And r theta is the familiar 2 by 2 matrix with cosine of theta and minus sine of theta in the first row and sine of theta and cosine of theta in the second row. Now, suppose we change the basis. Let's define a new basis for the same vector space. We set e bar 1 equal to 1, 0, which is exactly the same as the old E1. And we set E bar 2 equal to 1 and 1. The question is, what is the matrix representation of rotation by theta in the new basis? In the other word, what is R bar theta? To answer this question, we use A bar equal P times A times P inverse. So to define R bar theta, we need to change of basis matrix P. How we do find P? We take each of the old basis vector E1 and E2 and express them in terms of the new basis vector E bar 1 and E bar 2. First, E1 is equal to E bar 1, so its coordinate in the new basis are 1, 0. Second, E2 is equal to 0, 1, but notice that 0, 1 can be written as a E bar 2 minus E bar 1. So its coordinate in the new basis are minus 1 and 1. Now we build P by putting this coordinates vector as a clone. So P equal the matrix with first clone 1, 0 and the second clone minus 1, 1. From here we can also compute P inverse. Now we apply the formula R bar theta equals P times R theta times P inverse. Substituting the matrices into this equation, we can compute R bar theta directly. As you can see, R theta and R bar theta are two different matrices. They look different, but they are similar matrices because they are represent the same linear operator in two different bases. And if you agree with me, R bar theta actually looks a little more complicated than R theta. This shows an important point. By choosing a substitute basis, we can sometimes get a much simpler and nicer matrix representation of a linear operator. Let's pause here and put down a waypoint so we don't lose track of the big picture, the connection between linear algebra and linear control. Remember, when we linearize our nonlinear system in a state space equation, we arrive at a linear system of the form delta x dot equal a delta x plus b delta u, together with a linear equation for output. Here, both delta x dot and delta x live in Rn. The system can be viewed as a linear operator. In fact, we can think of our state space as a vector space in Rn defined over the real numbers as a field. The system matrix A, B, C, and D is the matrix representation of this linear operator. Now, notice sometimes these operators are expressed with respect to the standard basis. Where does this basis come from? It comes from our physical understanding of the system. For example, in the mechanical system, the state might include position, velocity, and acceleration. In an electrical system, it might include voltage, current, and impedance. Based on this physical knowledge, we write down the state space equation in the standard basis. Or as a control engineer, we don't always build this model ourselves. So the linear dynamic is a combination of linear operators in a state space with matrix representation A, B, C, and D. Now here is the key point. When we linearize around some operating trajectory, the resulting matrix can be very complicated. But mathematically, we know that we are free to change the basis of our vector space. And sometimes, by changing the basis, we can find a much simpler and more insightful matrix representation of the same linear operator. So, the natural question is it possible to choose basis that makes the representation nicer and simpler? The answer most of the time is yes. And during these two lectures, I want to put this idea into your mind. Sometimes by changing the basis of our vector space, we can make the matrix representation of our system more elegant and easier to work with. Here, the basis of vector space is equivalent to a state variable of your system. In the next two sessions, we will discuss how exactly we can find such a basis and how to use it to simplify our system representation. Thank you.